This is a sample of some phenolphthalein here, and you can see it's clear. Okay, there's some liquid inside, but you can't really see very much. You can't see very much of it. Okay, it's clear. All right. So I've got some vinegar here, and I'm gonna put some vinegar in the cup so you can kind of see. It's just regular household vinegar I bought at the grocery store. Okay,
Good, Tom. Good observation.
There's some vinegar.
I'm mad at Tom.
All right, so this is, I'm going to put a couple, this is a pretty concentrated solution of phenolphthalein. Phenolphthalein doesn't easily dissolve in water, and the acids we use in a high school lab anyway are mostly water. And so if we put this in here, you can see there's no color change, okay? It's just dissolving, that's all you see, okay? All right, let's get the light over here a little bit closer so you see what's going on. There we go. All right, now what I have here is some basic drain cleaner. All right. So as we put a few crystals of this basic drain cleaner, and you can start to see some color change.
Whoa! Holy cow! Oh my gosh, that's crazy. It's like food coloring.
Yep, kind of so, isn't it?
You think you could put that in your like water and make it pink and then drink it? Misha, we don't need your input. Oh, Misha. Whoa. What else we got? Holy cow.
It's only the little crystals that kind of... They're not dissolving.
Oh yeah, they are dissolving. It's just a slow process because of, well, just the nature of it. So we haven't neutralized it enough to see that color change yet. Okay. Somebody go get me a glass stirring. No! Gracious. Goose man, find me a glass stirring rod.
Come back! Oh gosh!
I just need one, thank you. Goose man, go sit down. Okay, so we're remember this is a weak acid. From our lab yesterday, you know that it takes a lot of acid to get to the point where we actually neutralize it. That was the whole point of the lab yesterday. Remember that?
You're right.
So I'm putting some more in here.
Holy cow! Pink lemonade.
So we finally got to the point now. Alright, so now we've neutralized the acid. This is actually basic. So this would be somewhere above about pH 8, somewhere. Okay? Might be way above it, but it's at least above. Are you playing with one of the glass stirring rods?
No, I'm not playing with it.
Go put it up. Now.
Yes, sir.
Thank you.
Yeah, no problem.
So that's not yet to the
Too bad your mom isn't in here.
So Mr. Tatter, that's not yet to the dark pink of above 10 or whatever?
Probably not that high yet. Yeah, probably not. That's why I'm saying it's probably around maybe 9, something like that. If you get it really basic, it'll get a little bit darker than that. Well, it depends on how much I have in there too. I have it in a white cup, so it might get pretty dark if I have enough phenolphthalein in there, as well as having it a really high pH.
Make sure you use a lot of water to drink.
Yeah.
Mr. Tatter.
Brian, please sit down.
Where's the glass string rod?
Brian, do you not know where they go?
No.
Gooseman, would you help Brian out, please?
Oh, no.
Okay, Now, in earlier units, we learned about how to tell when you have an acid based on the formula. Okay? And we said that all Arrhenius acids, that's the simplest kind of acid, all Arrhenius acids will have a hydrogen on the front of the formula. Okay? So, and in fact, that's the way we dealt with it anyway. Now, we also learned in this class that you have some organic acids, and we usually put the formula for the organic acid had the hydrogen on the back, the one that does the work. But an acid is really an acid only when it dissociates hydrogen ions. At least it's only an Arrhenius acid when it dissociates hydrogen ions. So this, excuse me, the simplest definition of acids is Arrhenius, and Arrhenius says that an acid is an acid because when you put it in water, it gives away hydrogen ions. Okay? So that makes this an Arrhenius acid because it's giving away hydrogen ions. Okay? So that's Arrhenius. And Arrhenius says that bases are those substances that, when you put them in water, like the drain cleaner I just used, because that's the chemical in the drain cleaner there, you put it in water, it gives away hydroxide ions. Okay? Now we know a lot more about acids than Arrhenius did at the time he came up with this, and we know that acids can actually have acid behavior when they're in things that aren't water. If I'm working with organic substances, I might have to have something that's not polar like water, and in which case I need to have an acid that functions well in an organic or non-polar environment. And so it doesn't have to have water, but the only thing we're going to be using in this class, and that's the case with most high school classes, is that we're talking about what happens in water. Okay? Regardless, when you give away hydrogen ions, that's Arrhenius acid. When you give away hydroxide ions, that's an Arrhenius base. That make sense?
Yeah.
So that's Arrhenius. Pretty simple.
Spell Arrhenius? How do you spell that?
Like Uranus.
No, and please.
Like Uranus?
Yeah, this is what pirates say.
Arg. No.
That's a female yard bird.
Hen.
Me
No. I.
and everybody.
I am not the fellow.
Okay. All right. Then we've got another acid definition, which is used a lot more widely now, and that's called Bronsted
I heard that said Brian. I was like, oh. Wait.
Lowry, and that's two different people. I think this guy was Danish, and this guy was British. I'm not sure.
Do you spell this Bronsted with a 0?
It has an O with a slash through it. Okay.
Oh.
And I think one of them published a paper. No, yeah, one of them presented their acid-base theory at a conference between the two times when the other one submitted a paper for publication and it was published. So they gave them both the name. They basically give them credit by calling it Bronsted-Lowry. And what Bronsted-Lowry says is that we don't just give up hydrogen ions. We give the hydrogen ion to something else. So if I'm like putting hydrochloric acid in water, we would write it, gas maybe, I'd write it like this. Okay? And what's going to happen is the hydrogen ion is going to be given to the water molecule. And so what we end up then with is this thing we call hydronium.
Whoa.
This is called the hydronium ion. And what remains then is just the Cl ion. Okay? And so that would be a Bronsted acid. Okay? So this stuff, hydrochloric acid, is a Bronsted acid. And basically, if it's an Arrhenius acid, it's every kind of acid. But there are some Bronsted-Lowry acids or bases that are not Arrhenius acids or bases. Okay? And I'll give you an example of that in a minute. Let's look at... Now, Bronsted also says that the definition of a base is a little different. A base in the Bronsted-Lowry theory is anything that accepts a hydrogen ion. So it's not enough that it gives away hydroxides. That might make it a base. Okay? If I have this hydroxide ion in water, and I have hydrogen ions from some acid, then that's going to accept that hydrogen ion to make a water. So here's the Bronsted acid because it donates a hydrogen ion. Here's the Bronsted base because it accepts that hydrogen ion. Yes?
So what is water?
Water's both. Water's an acid and a base in the Bronsted-Lowry system. Okay? And in fact, it can behave like an acid or base in certain circumstances. Okay? Now that's a pretty uncommon way of thinking about it, but here's another common way of thinking. Here's a way of thinking about it too. If I have ammonia, which is a gas, and I put it in water, H2O, okay, what's going to happen is that at least some of these ammonia molecules are going to accept a hydrogen ion from the water. And this is where it's a lot easier if we write water as HOH, because you can kind of see where it's going. We can say that this one of these hydrogen ions is going to leave here and join up with the ammonia. Okay? And so what we're going to get then is NH4 with a plus charge. There's your ammonium ion. You can look up on your common ions list and see it. And then you have what's left is the hydroxide ion from the water. Okay? So that makes this an Arrhenius base because it accepts a hydrogen ion. While it cannot be this is a Bronsted-Lowry base because it accepts a hydrogen ion, but it cannot be an Arrhenius base because there's no hydroxide for it to give away. It actually ends up producing a hydroxide ion, but it doesn't have one to give away. Does that make sense? Mm-hmm. Okay. Now these are the only two theories that you have to work with in here. In this class, we're not going to do any calculations or determination of acids and bases for the third theory that I'm going to present to you. You just have to know what it is. I just simply want you to be aware of the third acid-base theory, and that's the Lewis theory. Okay? Now, in the Arrhenius theory, an acid is an acid because it gives away hydrogen ions. A base is a base because it gives away hydroxide ions in a water solution. Bronsted-Lowry says an acid is an acid because it donates a hydrogen ion to something. Okay? The hydrogen ion goes from one place and joins up with another substance somewhere and makes a new substance. Okay? And then a base is anything that accepts that hydrogen ion. And we're going to get back to this and we're going to define some things called conjugate acids and bases in a minute. But I first want to talk about the Lewis theory. Okay? The Lewis theory, remember Lewis? He's the guy that came up with the Lewis dots. Remember that stuff? Lewis structures or Lewis formulas, okay? So you can imagine it wouldn't be too much of a stretch that Lewis defined acids in terms of electrons. Okay? So let's use Lewis dots to explain what's going on with Lewis, the Lewis theory of acids and bases, okay?
Right.
Let's see. So if I have hydrochloric acid, I can write it like this. Okay, there's our Lewis dot formula for hydrochloric acid. And here's a Lewis dot formula for water. Okay, so we're putting those together. And as a result of putting them together, this hydrogen ion leaves this covalent structure and joins up with the water. And that just leaves the chloride ion all by its lonely little self over here. Okay? Now the Lewis theory says an acid is anything that accepts, an acid is anything that accepts a pair of electrons in a covalent bond. An acid is anything that accepts a pair of electrons in a covalent bond. Now that doesn't mean it's sharing an electron. It doesn't doesn't have one electron that it shares with another. So when we were writing Lewis formulas back in, what was it, Unit 3 maybe? Yeah. Unit 4, Unit 3. We showed the sharing arrangements, right? Lewis doesn't just skips over that sharing arrangement entirely, because both of the electrons that a Lewis acid shares comes from something else. It doesn't take any electrons and share them. It goes and just shares an existing pair. All right, let's take a look. This hydrogen ion right here is going to leave. Okay, there it is. It's a hydrogen ion. All right, it leaves behind the electron pair. It's not going to take it with it. Okay, so that hydrogen ion then goes over here and shares this pair of electrons. And that's what we make over here. All right? So because the hydrogen ion came from this species, this hydrogen chloride species, this is the Lewis acid. Because this is where the hydrogen ion came from that then shared a pair of electrons from somewhere else. Does that make sense?
What did you say an acid is anything that
accepts a pair of electrons from some other species in a covalent bond. And so this is actually a covalent bond right here we formed. There's the covalent bond with a shared pair of electrons. Okay? Now in the Lewis theory, this is the base because it donated the pair of electrons. It donated the pair of electrons to a covalent bond. Now it didn't donate one electron. That's not a Lewis base. It's only a Lewis base when it donates a pair of electrons to a covalent bond. Does that make sense?
So it's a Bronsted base?
This is what? Bronsted-Lowry is a different one. This is Lewis we're talking about now. So a Bronsted acid is anything that accepts a pair of electrons in a covalent bond. Okay, it doesn't accept one electron and share. It accepts a pair of electrons in a covalent bond. And a Bronsted base is anything that that donates a pair of electrons, not one electron, but a pair of electrons to a covalent bond. Does that make sense? Now, all I need you to understand about Lewis is the theory. Okay? You don't have to figure out if something is a Lewis acid or base based on its behavior in a chemical reaction. That's beyond the scope of this class. All I want you to know is the theory. We're going to be working with Bronsted-Lowry a great deal in here. In fact, in this unit, this is the primary acid-base theory we're going to work with. Okay? We'll work with Arrhenius sometimes because it's simpler, it's faster, but most of the time we're dealing with Bronsted and Lowry. Okay? Any questions about the basic theories? Yep.
Which one would be the acid
In the Lewis theory, this is the acid because this is where the hydrogen ion comes from that does what we said it's supposed to do, which is to accept a pair of electrons in a covalent bond. Okay? This is the base, water is the base, because it donates that pair of electrons to that covalent bond. Does that make sense?
Yeah, I guess it was just kind of confusing because that one's not accepting it.
This one? Well, this is donating. This is accepting. Acid, base. It's donating it to that bond. It's not giving away donating, but it provides the pair of electrons.
I know, but the other one, how is it accepting anything if it's giving it away?
Well, the hydrogen ion is being given away, yeah. But the hydrogen ion then accepts that pair of electrons into a covalent bond, right?
So it's the hydrogen ion and not the...
Yeah, that's one way to think about it. But we not only consider this to be the Arrhenius acid, but the whole thing it came from is also the Arrhenius acid because it's where it came from. All right? That makes sense to everybody?
What about the product?
Well, they have to do something to become acids and bases. So both Bronsted-Lowry and Lewis are more about the process than about just what it is. Arrhenius is kind of like, this is it because it donates these things. Boom, we're done. Bronsted, Lowry, and Lewis are more about the whole process overall as defining acids in that way, because acids are acids because of what they do. Okay? Now, one of the neat things about Lewis is it allows us to define salts. Some salts would be considered acids or bases. Just basic salts. Okay? And we're not going to get into that. That's a little too far, too advanced for this level of class. Huh? Yeah, beyond the scope of class. Okay? We are going to be dealing with this a lot. Okay? So, when we were talking about acids and bases previously, we would not have called ammonia a base. But it is. But it is, in this case, it actually produces hydroxide ions that do the work of a base.
You're right.
All right?
Okay.
You got the definitions down? So your written definitions are on your unit handout. But this is I hope I've explained in a more conceptual way how this works. Now, all acids and bases neutralize each other. All acids and bases neutralize each other. So if you put an acid with a base, you're going to get a neutral substance. Or you could get a neutral substance, depending on what the mixture is. And that's part of what this unit is about. Before we go too far, though, let me just tell you on page 9 of your unit handout are the strong acids you have to know about and the strong bases you have to know about. You just have to memorize those. Okay? Now, I can give you a trick for recognizing the strong acids if you'd like.
Yeah, let's do it.
Want the trick?
Yeah.
Okay. You can memorize them if you like memorization. 1, 2, 3, 4, 5, 6, 7. All right. Or I can just give you a little trick for knowing how to tell when you have a strong acid or base. All right. We got to divide it into two different categories. One is this side over here, which is the binary acids.
Okay.
A binary acid is strong if it's if the hydrogen is bonded to one of the halogens in the middle.
Okay.
We'll look on the periodic table.
Okay.
You got your test references out?
Get my periodic table.
Get out your test references. Get out your periodic table. So when I say a binary acid, meaning two elements, not necessarily two not necessarily two atoms, but two elements, is strong when it's bonded to one of the halogens. That's the elements in this column right here.
This starts with L.
Okay? Yes, starts with fluorine. Bonded to one of the halogens in the middle. Well, these two are on the end right here, fluorine and acetine.
Okay.
The ones in the middle are chlorine, bromine, and iodine. There are your three strong acids. Got that? All right, so that's a little trick for knowing what the strong binary acids are. Now, if it's not a binary acid, if it's an oxyacid, notice these all have oxygen in them. You can tell if it's a strong acid if you have two or more oxygens than you have hydrogens in the formula. Two or more oxygens than you have hydrogens in the formula.
Oh, because they all have more oxygen.
Yes. So notice this is nitric acid. It has three oxygens. That's two more oxygens than it has the one little hydrogen here. Okay? Sulfuric acid. 4 oxygens, 2 hydrogens. That's 2 more oxygens than hydrogens. This is chloric acid. 2 more oxygens than hydrogens. Perchloric acid. 3 more oxygens than hydrogens. Okay? So those are your strong acids and there's strong bases down here. And the strong bases you just kind of have to memorize.
What's the trick for them?
There's really not a good trick for that one. But notice these are all the strong bases are bonded to alkali metals or alkaline earth metals, but you have to know which one. Okay? They're not bonded to anything that's a transition metal. Okay? Now, if you can come up with a really good way to, shortcut for that, that's great.
They're all in the first two.
Yeah, alkali. They're in the first two columns. Alkali metals or alkaline earth metals and not transition metals. Exactly. Okay? Right, but I don't have a really good way to.
Why is there a missing element up there?
I don't know.
Somebody not turn one in?
I'm guessing Trotter stole it. I don't know. I don't have a clue.
Two?
No, nothing. No, I'm just joking.
You joker.
Yeah.
Crazy boy.
Yeah. All right. Let's see. Now pH. This was your extra credit question.
Right?
I didn't understand it. I get
Wait,
Oh, no.
we got an extra credit question?
On the who's not taking the test?
You want me to step out?
No. I just can't.